right. Hello, everyone. Thank you for being here. On behalf of the Environmental Finance Center Network, welcome to part 2 of our virtual workshop, Water Quality in the Distribution System. My name is Kristen Crew from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the training today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it in the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. GoToWebinar has recently gone through an update, and you can now add live captions, raise your hand, or react using emojis. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This training has been approved for 4.5 hours of drinking water continuing education credit in Ohio and Wisconsin, as well as 4 hours in Michigan and Indiana. All attendees will also receive a certificate of attendance for their personal record. To receive credits or a certificate for the session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or if you need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. And on that note, we can go ahead and get started. I would like to introduce our presenter for today, Daryl Gotham. He's joining us from the Great Lakes Environmental Infrastructure Center. Welcome, Daryl, and I will go ahead and pass it over to you.
Thank you, Kristen.
Can we get access to share our screen?
All right. Thank you, Kristen. So thank you all for returning today for the second day. What are we going to cover today? We're going to look at disinfection and disinfection byproducts. We're going to look at some of the elements of a sanitary survey, and we'll talk about sampling and monitoring. All right, so chlorine disinfection and disinfection byproducts. I like this slide. It shows some of the benefits of chlorine disinfection. I think it also shows just some of the improvements that we've made throughout time in just using more sanitary procedures and things. So if we look at this, we've got as we can see, we had in the 20s and as a rate of per 100,000 people that would die of typhoid fever in the past, and so we've gotten that down to pretty much it doesn't happen now. There were thousands of cases in the past. Nobody really understood why, what was causing it, and then in the 1670s, we first were able to observe microbes using a microscope. So that made us aware that there were these little things that, were out there. In 1854, John Snow figured out that cholera was caused by a waterborne disease epidemic. That's a very interesting study out of London. John Snow and the Broad Street Pump cholera outbreak. There's a couple of books that were written about it. If you're interested in reading more, The Strange Case of the Broad Street Pump is one of those, and The Ghost Map is another. But that was some really informative work that he did towards stopping a lot of disease. In the 1860s, Louis Pasteur developed the germ theory, and that theory was that microorganisms such as bacteria and viruses are the primary causes of disease. And then in 1908, New Jersey, they installed the first system in the U.S. to chlorinate drinking water. So if we look at our chart here, we show that there's in 1908, we were over 20, probably 25, 26 deaths per 100,000 people. And then you can see the decline in the years after that. And in 1945, we achieved less than 1 death per 100,000 people. So it's important. Disinfection, chlorination, very important stuff in the water industry. So when we look at the different bugs out there, the microorganisms, we consider them pathogens, and pathogens are disease-causing microorganisms, bacteria, viruses, parasites, things like that, and they can contaminate our water supplies, and they make people sick and possibly even kill them. So that's why we need to disinfect and chlorinate. We'll talk about coliform, and coliform is the total coliform, the testing that we do initially in our distribution system at our plants. That's an indicator organism. It doesn't say that just because we have those doesn't mean that there's that we have E. coli or fecal coliform, the things that are really dangerous. It doesn't necessarily mean that, but it means that we have an environment that is capable of sustaining that type of life. So the presence of coliform may indicate that contamination has entered the water. It could be different things. It could be bacteria, viruses, protozoa. And E. coli is an MCL. It's a maximum contaminant level. There's violations for that under the revised total coliform rule. So another thing that we can look at that provides a similar type of information as coliform is heterotrophic bacteria counts. And so they indicate that, once again, that there's stuff in the background, that there's activity going on that could cause some issues. And so if we've got a high counts in our water, they reference 500 CFU, that's coliform forming units per milliliter. That means that your water quality is probably not what it should be. It doesn't mean that there's a violation, but once again, it's an indicator that there could be a problem. And what could cause an increase in heterotrophic bacteria, or what does that increase signify? And it's it could be an early warning sign that there is a problem out there. Could be biofilm growth. You would probably also want to look into it further as far as coliforms. Maybe there's something out in your distribution system or in your treatment that is allowing that contamination to enter, and so it signifies that maybe we need to look a little further into this as a potential problem. And so what can we do as distribution system operators to protect our distribution system? And the two most important things that we can do are maintain a positive water pressure. If we maintain positive water pressure, as Greg talked about, the opportunity for backflow or back siphonage are much less. And also, maintaining the physical integrity of this distribution system. If we don't have broken pipes, if we don't have leaks, once again, that helps with making sure that our distribution system is protected. This photo depicts the idea that there's a pipe with a hole in it, and under normal circumstances, that pipe likely just the water goes from the inside out. There's adequate pressure to not allow the water from the outside of the pipe in, but under a low or negative pressure situation, there's always there's the possibility that water that contaminated with E. coli, that water on the outside with low or no pressure would enter into the pipe and potentially impact our system. And then having a free chlorine residual it's kind of it's a safety thing. And it's a a backup. It allows us to have a little bit of reassurance that if something like this were to happen in our system, that hopefully that chlorine could act on any of the water the contaminated water that might enter through a hole in the pipe. And then, but that's only going to take us so far. At some point, we'll use that chlorine up and we won't have any additional backup or safety remaining. All right, so we're into our first poll already. Which of the following could indicate that contamination may have entered the drinking water system? A, increase in heterotrophic plate count bacteria. B, the presence of coliform bacteria. C, decrease in disinfection residual. Or D, all of the above.
All right, it looks like the majority of people have gotten their answers in, but I'll give everyone just a couple more seconds to get those answers in before I close the poll. All right, closing the poll in 3, 2, 1. All right, Daryl, so the majority of people at 88% said D, all of the above.
All right, thank you, Kristen. Yes, D, all of the above is the correct answer. And we can explain that through A and B are the increase in HPC count, the presence of coliform bacteria. We indicated that both of those things are indicators of potential issues in the distribution system in the water. And then a decrease in disinfection residual, that could mean that our chlorine is working on some bugs that were introduced into the system. So all of the above would be the correct answer. So now we're going to look at some of the different disinfection types, chlorine specifically. So we've got chlorine gas. Chlorine gas, some of the great things about that is it's 100% strength available. So it's very, very potent. There are some issues. There's some issues with chlorine gas. It can be very dangerous. You see here a chlorine gas plume. Everything around there will be dead. Chlorine is a powerful oxidizer, and it would anything organic is going to be pretty much killed. So one of the reasons that more systems don't use that is because of all there's a bunch of regulations that are involved with operating gas chlorine. It's a safety thing. Some communities don't even want to consider it. So it's a great way to chlorinate, but it comes with its downsides. Liquid chlorine or sodium hypochlorite is probably the most common. It's the simplest. It's already in a liquid form. We're trying to add this to water, so it already is in a liquid, so it's easy to mix. But you'll note that the concentrations are lower, and it tends to come in. The concentrations will decrease through time a little faster than it will for gas, or for the solid, which is calcium hypochlorite, or HDH. And you see that that's got a higher strength, but these things tend to come in powders, or I believe they call these pucks, what we're seeing here. And so we've got to dissolve those. There's a little bit more goes into it. So they're usually, they're not as common. I think these are quite often used for chlorinating pools and things of that nature. I've seen them used in chlorinating water mains and things like that, but for day-to-day use as a disinfectant, it's not all that common. So our free chlorine residual in water is found in two different forms. It's found in hypochlorous acid, and it's found as a hypochlorite ion. We'll talk more about that in a future slide. And then we've got another form of chlorine disinfectant is chloramines, and that's where we take 5 parts of chlorine to 1 part of ammonia, and we add that together. It can be measured as a combined or a total residual versus a free residual. And chloramination is when we add ammonia is added to water that's been treated with chlorine. The ammonia acts with the hypochlorous acid in the water, forming this long-lasting disinfectant. So one of the benefits is it lasts a long time. Now, we'll see as we go through that it has its downsides as well. So I mentioned the idea of hypochlorous acid and the chloride ion. Free chlorine is going to be in both forms. The portion of each is going to depend on the pH. So if we look along here, this curve changes as the pH changes. So, you know, at a pH of 5.5, we have pretty much 100% of it is hypochlorous acid, and at a pH of 10, almost 100% of it is going to be chloride ion. And so, ideally, we want to have more of that hypochlorous acid because it's got a, you know, it's more able to react with any coliforms or any bugs in our system. It'll take on those pathogens more effectively. So at a pH of 7, we're seeing about 80% hypochlorous and about 20% hypochlorite. So that's a good mixture. So here we have one of my favorite things, and I believe one of the things that when I've talked to operators, it's one of the hardest concepts to get them to understand. It's counterintuitive. It goes against what we would normally think, but it's the idea of breakpoint chlorination and this breakpoint curve. So as we go along, on the bottom we're adding chlorine, and on the side we're seeing what the result is in chlorine residual. So initially, if we're starting out and we're adding chlorine at a well, say, and we're looking for what our residuals are, initially we're going to add chlorine and we're not going to really see anything. The chlorine is destroyed by reducing compounds that are in the water initially. So we'll add chlorine and nothing seems to happen as far as the residual goes. And then we start to see this, as we continue to add, we start to see this curve and it goes up. And during that, we're forming chlororganics and chloramines. And these are the things that give us the odors, the chlorine odor. Taste and odor concerns come out of this. And so we're adding chlorine and we're just getting more of the stuff we don't want. And so we get complaints. And so as a state regulator, I would go out to systems and I'd tell them, you need to increase your chlorine residual. And they'd be like, well, you know, we do that and we just get more complaints. And so they're hesitant to do that. But the part that they weren't understanding is that we need to keep that process going. And so as we get through that, we produce those chloramines, and then we get to the next stage where that chlorine is going to destroy those chloramines. And so we see a drop in our chlorine residual as we continue to add chlorine. But we get to this important spot right here, this break point. So we get to breakpoint chlorination, and then after that, all the chlorine that we apply becomes available as free. So if you can get past the odors and you can get through this, you'll get to the point where now we're adding free chlorine, and that's what we're looking for. That's the stuff that we need out in our distribution system. So so the dose is going to be equal to the demand plus the residual, and the total residual is a combination of the combined and the free residuals. So that kind of is a little better depicted here. Total residual is equal to the free residual and the combined. All right, so in this instance, we have 0.2 parts per million to get. That's where it takes for the chlorine to use up those reducing compounds in this example. And then on top of that, we have 0.3 parts per million of combined chlorine. And so those two together result in a half a part per million of total demand. And then in this instance, we might have another 1 part per million of free chlorine residual on top of that. And so our chlorine dosage, in order to achieve 1 part per million, we need to apply 1.5 parts per million to get to that point, because 0.2 is used up by reducing compounds, 0.3 is combined. So that requires 1.5 to get to our free chlorine residual goal of 1 part per million. So our dosage is equal to the free residual plus the demand. Now the demand is made up of both the reducing compound, what's used for the reducing compound, and the combined chlorine. So now we are on to poll number 2. What dosage should be applied to drinking water with a total demand of 0.4 parts per million if the intended free residual is 1.2 part per million?
All right, the majority of people have their answers in, but I'll give everyone just a couple more seconds to get those in, and then I'll close the poll. Closing in 3, 2, 1. All right, Daryl. So the majority of people at 80% said D, 1.6.
Okay. Yeah, I'm amazed that this class is put towards Ohio operators. Now Ohio operators are fast to respond. They're used to this process. So let's look at this. So 1.6. So D is the correct answer. And so how do we get to that? So we take and we have our dose is going to be equal to that demand plus the residual. So in this case, the demand was 0.4 parts per million, and our residual was 1.2. So that gives us a total of 1.6 parts per million. All right. So now we're going to talk about the pounds formula again. So this is it's really important when it comes to how we figure out how much chlorine to apply. So we'll go through this again today. And this just shows it shows what gas chlorine might look like, some of the components. This is the regulator here, or excuse me, the rotometer here. And the rotometer provides us units in pounds per day. So this is a setting. So we need to know how many pounds we need in order to set this rotometer so that it applies the right amount. So we need to figure that out. So we use the pounds formula to do that. So we've got an example where the question is, what is the feed rate setting for gas chlorine in pounds per day if the plant flow 1.2 million gallons a day and the required dosage concentration is 1.5 parts per million? So to solve this, we're gonna plug that 1.2 mgd in for the flow, and then we'll take the concentration of 1.5 parts per million, and we're gonna put them into our equation for our pounds formula. If we do that, it tells us that it's going to take 15 pounds per day for us to have a dosage of 1.5 parts per million with our flow of 1.2 million gallons a day. Now for sodium hypochlorite, for liquid chlorine, it's a little different. It's different because the concentration isn't 100%. So for gas chlorine, there's things we don't have. It's a much simpler calculation because we're using 100% strength. So we have to take into consideration for liquid chlorine the fact that it isn't 100%. The top part of the equation is just determining the pure chlorine, just as if it were gas chlorine. Now we'll divide by the percent strength to take that into account, and that gives us the weight of sodium hypochlorite liquid actually needed. And then we also need to divide by the weight per gallon, and that's going to give us the number of gallons that we need per day. We could do it in pounds. Some people operate in pounds because then they have scales and they can do it that way, but most people are going to want to know how many gallons of liquid chlorine they need to apply. So that's what we put that into the formula in order to take that into account. So then our formula becomes the gallons per day is equal to the million gallons a day times the concentration times 8.34 pounds per gallon. And then we divide by that percent strength, and we multiply by the specific gravity. So the specific gravity is the comparison of a liquid to the weight of water. So that we compare those two, and then we multiply that by 8.34 pounds per gallon. So that gives us the weight per gallon there. So let's look at an example of that and use our formula. So what is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2 when the plant flow is 500,000 gallons a day and the dosage is 0.9 parts per million? Now keep in mind, specific gravity, it's a comparison to water. So water is 1. So if it has a specific gravity of 1.2, that means that liquid chlorine is heavier than water. If it was less than 1, it would mean that it was lighter than water. So for our solution, we're gonna use the formula. We're gonna plug in those values, and we'll see what we get here. So our formula is gallons per day is equal to the flow times the concentration times 8.34 pounds per gallon times the percent strength times the specific gravity times 8.34 pounds per gallon. So if we put that in, we've got a 500,000 gallon a day flow, 9/10 of a part per million concentration, and we've got our percent strength. We're going to convert that percent into a decimal, so that becomes 0.125. Our specific gravity is 1.2. So if we multiply that out, we get around 3 gallons per day. So we would need about 3 gallons a day in order to make that the concentration based on our flows and our chlorine. So this is an LMI pump, one of the more common types of pumps that we would see in small systems, especially groundwater systems that are adding chemicals. And the pump is we can vary how the pump operates based off the speed, how quickly it operates, and then the stroke, how long, how much chemical goes in with each time the pump operates, or each stroke of the pump. And if we look at this in a little more detail, it shows that this pump has a max flow of 0.58 gallons per hour, and at a pressure of up to 250 psi. And that's when so that max is when both the speed and the stroke are set at 100%. So that pump is going as fast as it possibly can, and we'll get just under 0.6 gallons per hour. So if we want to look at what kind of output our pump's going to have, a chemical feed pump is rated for a maximum flow of 0.58 gallons per hour. What is the actual output of the pump if both the stroke and the speed are set at 70%? So the actual output is going to be equal to the max output multiplied by this percent stroke and the percent speed. So our percent stroke and our percent speed are both 70%, so we're going to use 0.7 in each of those. So we'll take our 0.58 gallons per hour and multiply that by 0.7 for our speed and 0.7 for our stroke, and that gives us 0.284 gallons per hour. So that's how much at 70% speed and 70% stroke that we would be able to pump from that pump. And that's a pretty good set point for our pump. I mean, if we were to design a pump, we'd want, it's great to be about half of day to day, be about half of what we need. That way we have room to move that pump up or down depending on what the conditions that we might find or the flows that we're using. So that 0.284 is about half of what the pump, the 0.58 that the pump is possible of or capable of producing. Now, if we want to know how many gallons that we can put out in a day, we could just take that 0.284 gallons per hour times 24 hours a day. That tells us that at our 70% stroke and 70% speed with this pump, we'd be putting out about 6.82 gallons per day of chemical. And we use that compared to the feed rate calculation for the chemical or for chlorine. So poll number 3, calculate the free chlorine residual given a flow of 0.8 mgd, a gas chlorine free feed rate of 13.4 pounds per day, and total chlorine demand of a 0.5 part per million.
All right, just over 60% of people have put in their answers. I'll give everyone just a little bit more time. All right, the majority of people have voted. I'll close the poll in just a couple seconds. All right, closing the poll in 3, 2, 1. All right, Daryl. So we had the majority at 59% voted for B, 1.5. We had also over or almost a quarter of people at 22% did vote for A as well at 2.
Okay. All right. Thank you, Kristen. Yeah, it's a lot of pressure to get these problems done in a timely fashion, I understand. So yeah, the answer is 1.5 parts per million. And how do we get it? How do we come up with that? So the first thing we do is we're going to solve for the dose. So we take our 13.4 pounds per day, we divide it by our 0.8 mgd times 8.34. So that's going to tell us that we need about our dose is going to be about 2 parts per million. So that's how much we're aiming for to apply or dose. And then the residual is going to be the dose minus the demand. And we know that if our dose is 2 parts per million and our demand is a 1/2 part per million, we subtract the demand from the dose, and that tells us we have 1.5 parts per million that's what our residual should be. All right, so we've talked about, we've got these different pathogens, and one of the interesting things is that when we're chlorinating, when we're disinfecting with pathogens, the virus and the protozoa, we don't look to necessarily kill those. Sometimes that's not capable, but if we can render them useless so that they can't replicate, they can't reproduce, then we've done our job. Typically with things like bacteria, we actually do kill those, but with viruses and protozoan, we're happy if we can just inactivate them. And so that means if they can't reproduce, they can't cause any more problems. And the two most important things as far as chlorine disinfection goes are that it's that concentration, the concentration of our residuals, and then how much time does that residual have to work on the water. And so that's going to drive a lot of what we do as far as determining if we're meeting our compliance requirements. So for different types of treatment, the regulations require that we different log virus inactivations. And this is this chart here is it's a comparison of our what we need to. It tells us how much we need to have, how much chlorine residual we need to have based on our conditions in order to inactivate the viruses. So it gives us our minimum amount of CT, which is that concentration times the time that we have. So in this case, 4-log removal is 99.99%. 3-log removal would be 99.9%. So that's the log is that how many digits we have there. So if we look at this, both the temperature and the pH are important when we look at these tables. These tables tell us how much CT we need to have. So if we have a temperature of 10 degrees Celsius and we have a pH of 7.5, that means that pH is in this range and the temperature is set here. That means that we need to have a CT of 6 milligram per liter. That's how we note these CTs is in minutes per milligram liters. You'll note here that as the temperature drops, so does the amount of CT that we need. As the pH increases, we need to have more. We go at the same temperature, we would go from a CT of 6 to a CT of 45 if we change the pH. So 1 milligram, 1 part per million times 6 minutes. So if we had a concentration of 1 part per million, and we would need 6 minutes in order to achieve that 6 minute milligram per liter. Excuse me. And that's at the first service connection. So if we look at this simple groundwater system where we're disinfecting, where the disinfection point is here, we've got chlorine, disinfects here. Where we're talking about having to meet that requirement is before it gets to our first customer out here in the distribution system. So that's where our CT is determined from this point of disinfection. That's the time until it gets to that first customer. So that's the time component. Concentration we can figure out based off of our residuals that we collect. So we'll do an example problem here to determine the CT at the first connection. So we've got a groundwater system. Their requirement from the 4-log removal table is a CT value of 6 milligram per minute, 6 milligram minute per liter at the first service connection. All right, so we know there's 500 feet of 8-inch pipe between the disinfection point in our well house and that first connection, and the flow is 250 gallons per minute. The free chlorine residual is 1.5 parts per million. All right, so this is a multi-step problem. The first thing that we want to do is we want to convert the flow from gallons per minute to cubic feet per second. So dividing by 7.48 gives us the cubic feet, and then dividing by 60 gives the flow in seconds. So the minutes will cancel out, the gallons will cancel out, and we end up with 0.557 cubic feet per second. And that's important because we've got our pipe is in feet and inches, so getting that from gallons to feet helps. So the next step, we're going to convert the pipe diameter from inches to feet. We divide by 12, so an 8-inch pipe is 0.67 feet in diameter. And next we find the area. So if we take 0.785 times that 0.67 times 0.67, that gives us 0.35 square feet. So that's the cross-sectional area of our 8-inch pipe. Next thing we're going to do is we're going to take and divide the flow in CFS by that area that we just found so that we can get velocity. So we're going back to some of that basic math that we did yesterday when we do this problem. So we're going to divide our 0.557 cubic feet per second by the area, and that's going to give us our velocity. In this case, the velocity of that flow is 1.59 feet per second. Now we're going to take into consideration the 500 feet of pipe. So we're going to divide the linear foot of the pipe by the velocity to find the total contact time. So we had 500 foot of pipe and the velocity is 1.59 feet per second. That tells us that we've got about 314.5 seconds worth of contact time in that pipe, or the time that that water or that chlorine's in contact with it. And then it equals out to about 5.24 minutes if we divide that 60 seconds by, or the number of seconds by 60 seconds in a minute. And then we just compare that to what we were supposed to achieve. So we take into consideration our concentration of 1.5 along with the minutes. So it's the concentration times the time gives us that. So we multiply those two together, we get 7.86 milligram minutes per liter. Right. Minute, it should be minute milligram per liter, excuse me. So what we're saying is that number then, that 7.86 is greater than the 6 that we were required to have. And so we've achieved our compliance with that. And so we don't always, there's plenty of times where we're not just applying chlorine to the water that goes out in the distribution system. There will be opportunities as water operators where we need to disinfect water mains. It could be from either new main installation. It could be from a situation where we had a main break and we've done repairs, and so just reference this is American Water Works Association standard. These standards are great because they will give you a step-by-step procedure to follow to make sure that you're doing what you need to do in order to disinfect the water main. They've got these for all sorts of things, for different types of pipe installations, based off materials and things like that. One of the methods is continuous feed method. We won't necessarily go into details about these. I just want to make sure that everybody's aware that that they're out there, and they all pretty much involve the concept that we're going to put in highly chlorinated water. You know, in continuous feed, you're looking for a residual of at least 25 parts per million and 10 parts per million after 24-hour contact time. The tablet method, so that's going to use that HTH, the solid form. You're aiming for a free chlorine of 25 parts per million. I mean, these are all well above what we would want to have in a distribution system. And then the slug method is highly concentrated chlorine, 300 parts per million, with a 3-hour contact time. So the idea is that the contact time is shorter, but the concentration is higher. So it's kind of that CT, concentration times time. And it's important to keep in mind that after we use this highly chlorinated water, we can't just dump it out on the ground or into the storm or definitely not the sanitary system, because it can have detrimental effects. It can water at concentrations of 5 parts per million or greater can be toxic to plants. I would think that if we were discharging a 300 part per million water into our wastewater system, that's going to upset the wastewater treatment plant. And then there's other AWWA standards that are out there for different types of disinfecting. I mean, we could be disinfecting a storage tank. When you do that, you want to make sure that it's cleaned properly first, power washed and drained out. In this case, they're looking at 200 parts per million of chlorine and letting it sit for 3 hours. Rinse tank walls and drain it out. Dechlorinate that rinse water to make sure that we're not killing anything as we discharge it. And then you want to refill the tank and take back T samples. And the same thing with if you're repairing or or installing new main, replacing old main, you definitely want to collect the proper number of bacteria samples before, and the results coming back good before they're put into service. And for the same thing goes if we're to try and disinfect a well. Sometimes we've got a well driller and they do some work on a well, or maybe you had you're getting positive bacteria from a well, from the source. You may want to do some chlorinating, and this is generally how you might go through it. So wells should be disinfected with a dose of chlorine that results in 50 parts per million residual throughout a 24-hour period. Obviously, you don't want to just take that well that's in the water and pump it to the distribution system at those high levels. You need to calculate the volume of the water that's in the casing so that you know how much chlorine you're going to add. And then afterwards, we're gonna dechlorinate and flush that water out. You also need to collect negative bacteria samples to make sure that it's safe. And anytime you go through a process like this, I would recommend that you talk to your regulating agency, whether it's the state, if it's EPA, whoever that might be. They can help guide you through the process and make sure that what you're doing is correct. So let's look in more detail at a well disinfection example. So we've got a 10-inch diameter casing and our water column's 200 feet. We want to calculate the gallons of 12.5% bleach needed for a dose of 75 parts per million. So in this case, we're going to use 1.2 for the specific weight of the liquid chlorine. All right, so there's our well, 10-inch well with our 200-foot water column. So the first thing is we want to calculate the volume of the water in gallons. So how much water do we have in that? We want to convert our inches into feet so that we're working with the same units. So a 10-inch 10-inch well is 0.833 feet. Our volume in gallons, we take our formula for the volume of the cylinder, 0.785 times that 0.833 times 0.833. We multiply it by the height of that column of water, 200 feet, and then we multiply by 7.48 gallons per cubic feet so that we can convert from the unit of feet or cubic feet to gallons. We do that and we get just under 815 gallons. Next, we're going to convert that into million gallons so that we can use our formula for sodium hypochlorite, and we take that that 0.000815 million gallons, multiply it by that concentration that dose that we want to get, multiply by 8.34, and then we divide that all once again by the percent or the concentration of our bleach, multiply it by the specific gravity of the bleach, and by 8.34. We do all that, and it tells us that for that, based off these conditions, so if we've got a 10-inch well, 200 feet of water, we want a dose of 75 parts per million, and we're using 12.5% liquid chlorine, we're going to have 0.408 gallons of that in order to achieve those results. So poll number 4, I want to make sure that everybody understands that there's a little hint at the bottom of the slide in how to solve the problem. So I know when Kristen makes it live, you're going to lose that. So you may want to keep an eye on this little, maybe take a note. But the poll says a well with 8-inch casing has a water column of 350 feet. Calculate gallons of 12.5% liquid chlorine needed for a dose of 50 parts per million. The specific gravity is 1.2, and select the answer that's closest.
I'll hold off on a little bit before I launch the poll as well, Daryl.
Okay.
All right, I'm going to go ahead and launch the poll now. Okay, just over half of folks have voted, so I'll give everyone just a little bit more time. All right, we're at 90% of people that have put in their answers. So I'm going to go ahead and close the poll in 3, 2, 1. All right, Daryl. So the majority at 65% voted B, 0.31 gallons. And behind that at 25% of people said C, 0.67 gallons.
Okay, great. Thank you, Kristen. So the answer is B, 0.31 gallons. And how do we come up with that answer? All right. So we've got it all right out here. A well with an 8-inch diameter casing has a total water depth of 350 feet. We need to know the gallons of 12.5 bleach needed for a dose of 50 parts per million. So to get the units straight, we're going to convert inches to feet, divide by 12. The next thing we're going to do is we're going to take in that formula for the volume of our cylinder is here. Then we're going to multiply that by the depth of the water, and then we're going to multiply that by our conversion from cubic feet to gallons. Then we'll divide by that 1 million gallons divided by mg just to get it in, to get our mg into it. If we do all that, we've got 914.3 gallons divided by 1 million gallons, or 0.000914 mg. All right, so that's the number of million gallons we have. So then we use that sodium hypochlorite formula. We put that in, we multiply by the dose that we're looking for, that concentration we're looking for, and then multiply by 8.34 pounds per gallon. And then we divide that all by the 12.5% converted to a decimal. We multiply by specific gravity and then by 8.34. One of the things, a little hint here is that 1.2 liquid chlorine at 1.2 specific gravity, it can change based off the concentration a little bit. So if the concentration is a little lower, maybe the number's lower, but when you multiply the 1.2 for the specific gravity times the weight of water, it's roughly 10. So that's a good rule of thumb, is that 12.5% chlorine is about 10 pounds per gallon. So we go through this calculation, we come up with 0.305 gallons, and we round that up to 0.31. All right. So the next topic that we're going to talk about is disinfection byproducts. So we've been adding this chlorine to the water, and unfortunately, there's a downside to that. Chlorine is very important. We need to do it, but we also have to take into account the effects that it can have. And so what are disinfection byproducts and how do they form? So in the simplest sense, there's a lot of different potential sources, but if we look at this graphic and we look at the idea that it rains and the water runs across the ground and it picks up these organics. And in this situation, we have a surface water system where we're pulling water out of, say, a lake or a river, and we treat that water and it goes through the filters. And as you notice, the concentration, the number of these things kind of goes down. We're pulling a lot of the organics. The organics are the things that we're concerned with when it comes to disinfection byproducts. We're pulling them out as we filter this water out. But the downside is when we add chlorine, that chlorine will react with those organics they're naturally in the water. It'll form these disinfection byproducts. Okay, and so the disinfection byproducts go out into the system. We'll talk in further detail about them, but it can be harmful and so it's regulated. There's a maximum contaminant levels for those. And what are they? All right, so disinfection byproducts are made up of two major components. There's the total trihalomethanes, or TTHMs, and it's these four chemicals, and those combined, they call them total. So if you were to run a test on this, you'd get results for each one of these typically, and then they would give you a total of them. And so compliance is based off the total of them. So trihalomethanes are 4 volatile organic compounds found in drinking water. And the concern is they pose a risk of cancer if they're found over the maximum contaminant level of 0.08 parts per million. And so that's those combined, all 4 of them combined. Now, they're natural. I mean, they occur with reactions with natural stuff. So it's not necessarily anything that we did. The water just naturally has that stuff in it. And it's the reaction between that stuff, those organics and the chlorine. And the other component, there's 2, as I said. The other one is the haloacetic acids, and they call those HAA5. So there's 5 different haloacetic acids that make up the HAA5. And those are also weak acids. They pose a cancer risk when we find them above 0.06 parts per million. So that's the established MCL for those. In both of them, it's something that it's a reaction between the chlorine and naturally occurring things in the water. One of the things that's interesting about this rule's a little different than a lot of the others in that we're looking at a locational running annual average. So just for instance, you've got a system and they collect, you've got to collect 4 different sites out there in the distribution system. Well, they're going to look at each one of those sites individually for as far as determining compliance, and the compliance is going to be based off the previous 4 sets of results, the previous 4 quarters, say. And so it's an average of those. So there can be situations where you get a result that exceeds either of these 2 MCLs, but you didn't exceed the running annual average because you've got lower results that will bring that down. So it's kind of an interesting one. And if you're confused about how this works, you feel free to contact me. You could contact your regulating agency and they could help you maybe better understand it. But how do we stop the creation of THMs and HAs? So it's naturally in the water. A lot of the things that we do in the distribution system really can affect or help with that. So if you've got a storage tank, you can add a mixing component to the storage tank so that the water gets mixed thoroughly throughout there, and you don't end up with, and we'll show later, stagnant or we're not bypassing water. And you can ensure that tank turns over in 5 days or less. So if we've got a tank that we don't really use a lot of water out of it, it's more likely time will cause the chlorine has time to get in contact with this organics, then it's going to cause these formation. You could use chloramines as a disinfectant residual. As we said, they've got their own set of concerns too, but in situations, it may work for your situation individually. If you've got concerns with THMs and HAs, you may want to look at chloramines. We can flush our dead ends in areas where we don't use a lot of water. That can help because we're getting fresh water into those areas. We're taking out the water that maybe has sat there longer and has the potential to have formed these. And then if we can clean our tanks out, flush our mains to make sure there's no sediment or debris in those, that can also help minimize the formation of these. And there's at the bottom of the screen, there's a link to EPA guidance documents. Those are very helpful when it comes to understanding these rules. I'd encourage you all to look at these as they come out. We've got several of them on these. We've had them on the slides. So water age, we talked about the idea that you want to turn tanks over and things like that. Well, water age is the amount of days or hours that water is in the system. So to keep fresh water in the system, we want to minimize that water age. Where can we find that older water? Large diameter mains. They hold a lot of water. And there's always, if you don't have high flows, That water will sit in those mains. You've got areas where you don't have high usage. Maybe you did in the past, maybe in an industry and they went out and now the water just sits there. Dead ends are another opportunity, because the water, if you have a dead end, the only place to use it is at that end. And then you can have seasonal usage that can affect, maybe you're a community that has a lot of tourism in the summer but nothing in the winter. You get low usage in the winter. And then short circuiting we'll talk more about, but that quite often we see that in tanks. Now nitrification is something that comes up when we talk about it's a microbial process when the ammonia oxidizing bacteria convert ammonia into nitrite, and then that is then oxidized to nitrate by nitrite oxidizing bacteria. So we've gone through there's a two-step thing. And both of those nitrates and nitrites are regulated by EPA. And so they're not good. They can cause what's called blue baby syndrome to young infants. So we don't want that to happen. And nitrification, it can cause those high nitrate levels. We can see a loss of disinfection residual when we have nitrification, and we can have bacterial growth because nitrate is a food. So what can cause nitrification? So I said, chloramines might be an option, but it can also lead, use of chloramines can lead to this nitrification. So there's no silver bullet in any of these things. So it takes a good deal of consideration. Ammonia is a food source for bacteria. It's going to allow that food or the bacteria to grow because it's got food. Warmer temperatures can also lead to nitrification. If you've got sediments out in your distribution system, whether it's in your tanks or your mains, they can harbor bacteria. If you've seen a significant drop in pH and alkalinity, that can also affect that can lead to nitrification. And how do you solve it? Increase your disinfection residual. So if you get it out there, disinfection residual is going to help with bacteria. And then tank mixing and cycling. So make sure that we don't have that short circuiting. We don't have long retention times in tanks, and then keeping those tanks clean will also be helpful in avoiding nitrification. So I just mentioned dead ends. Dead ends are not a good thing. If we look at this is probably the worst distribution system out there. As we can see, we've got several dead ends. They're all circled here. Pretty much everything is a dead end here, and dead ends are not good because we see things like higher water age. Our chlorine residuals will drop. We can't maintain good chlorine residuals. Our sediments will build up because there's low flows in dead ends, and so any sediments are allowed to drop out into the mains. And accumulation of sediment can allow places for bacteria to grow, or biofilm. Stagnant water can lead to the formation of scales, and then these disinfection byproducts. So as we said, that it's a factor of how much time that the water's out there and the chlorine has to react with these organics. So this shows there was a study done that found that distribution systems with dead end and chlorine residuals less than 0.2 parts per million, or chloramine levels less than 0.5 part per million, had substantially more coliform occurrences system-wide than systems maintaining a higher residual. And it's difficult without flushing. You could flush these dead ends, but it's difficult without doing something like that in order to avoid low chlorine residuals in dead ends. And so there's another study that was done, the effects of residence time to water quality in large water distribution systems. So they found that the longer that we had water out there, that we have low velocities, you'd see both an increase in the HPC, heterotrophic plate count growth, and the levels of THM when we had increased water age. And that didn't matter whether you had, regardless of that, how much the chlorine residual levels were. And so the HPC, it estimates the number of bacteria, yeasts, and molds out there as well. So it's not just, it considers stuff beyond our typical pathogens. Chlorine residuals decreased with water age. So as we see here, the HPC counts go up as we go out. And the chlorine residuals, typically chlorine residuals are going to drop through time. It's just a normal way that operates. And so this graphic shows through time, so where your time is on the bottom, chlorine residuals and THMs are on the sides. As the chlorine residual drops through time, the TTHMs increase. So that's just the normal way that things operate. And then storage tank turnover. So the idea is that, we want to take and get fresh water into our tanks. We want to use the old water, the oldest water that's in there. We want to just move it through. That helps with a lot of these things. That helps increase our keep our residuals up, and it helps to avoid formation of disinfection byproducts. So ideally, we want to make sure that tank's turned over in less than 5 days. The idea is that the water that comes in today will be out of the tank within 5 days. But it's a balancing act, because we want to make sure that we have enough. If we've got an elevated storage tank and we're using that to, for fire flow, to satisfy our peak flows, we want to have, based on those things, we want to have a lot of storage. But we also don't want to have so much storage that we can't get this turnover. So if we look at a 500,000 gallon storage tank and it's got an average flow of 175,000 gallons a day, we can easily determine how, what's the turnover of our tank. And this is assuming that the water that comes in now, the oldest water leaves first, and which we'll look at mixing and things like that. And it's not always necessarily the case, but in the simplest form, to figure this out, we're going to convert that 0.5 mgd to gallons. We do that, we end up with, 500,000 gallons is 500,000 gallons. 500,000 gallons is 500,000 gallons. So, and then we divide that by we divide the volume by the flow. So we take our 500,000 gallons, we divide that 175,000 gallons a day, and we come up with a 2.86 days. So obviously that's less than 5 days. And that is also the assumption that all of that water is coming, that the first water in is the first water out, the last water in is the last water out. All right, so now we're on to poll number 5. I think we'll take 10 minutes. We'll start this poll and take 10 minutes for our break. The poll says, what are factors that can lead to increased disinfection byproduct production and loss of residual? A, tank turnover less than 5 days and excessive flushing. B, tank turnover greater than 5 days and sediment buildup. C, use of chloramines in system flushing. Or D, all of the above.
All right, Daryl, the poll is launched, and we'll all come back and join at 2:25 Eastern.
Sounds great. Thank you, Kristen.
Thanks, Daryl. All right, we'll be rejoining the session in just 2 minutes, just a 2-minute warning. All right, I'm going to go ahead and close the poll. And Daryl, we had only 2 answers were guessed. B, at 85% of people said B, tank turnover greater than 5 days and sediment buildup. And 15% of people, so 7 folks had guessed D, all of the above.
Okay. Yes, and the answer is B, tank turnover greater than 5 days and sediment buildup. So that would be a that would be a problem. It would lead to the disinfection byproduct production and loss of residual. Tank turnover less than 5 days, excessive flushing would be the opposite. So we would see less DPP production and higher residual. And then chloramines, we said, do not cause the formation of disinfection byproducts, so that C would not be the answer. So B is the correct answer. So I've talked a couple of times now about the idea of short circuiting and tank mixers, and so the concept is here. If I run through some of this stuff, as we see, for instance, we've got warmer, lighter water on the top of a tank, and we've got colder, heavier, denser water at the bottom. And in this instance, if we put the water in at the top, it's going to drop down to the bottom, and that bottom water, the cold water, is going to be the stuff that leaves first. So what happens is that we end up with this warm water that stays in the tank because it's lighter and it doesn't mix together. So we're short circuiting this tank. We can fix that in a couple of different ways. In this instance, we've got a mixer in the tank, and we're basically pushing that water around. We're getting it so that it's all very similar. The other thing in this one, it's an air. We're adding air to the tank, and that's pushing the water around, bubbling. And so if we can use methods like that. The other thing we could do is we could have baffles, so we can have things in the tank that force the water to go in a certain direction instead of just in the tank, down and out. There's a few different things that we can do. But tank mixers, they kind of homogenize that water. It's going to be all very similar, and it limits the disinfection byproduct formation. So what are the effects of disinfection on biofilm in relationships to DBPs? So as we see here, chlorine can reduce the biofilm growth rate. Sometimes it'll even destroy those biofilms. However, as we said, chlorine produces disinfection byproducts. And so these biofilms out in the distribution system can be another source of these organics that can cause DBPs. In a recent study, low disinfection byproduct formation was observed with a chlorine residual of a 0.5 part per million. When the residuals were increased to 2 parts per million, however, disinfection byproduct concentrations increased sharply and then decreased after 2 weeks. So what might have happened in that situation? So with the free chlorine at 2 parts per million, it was effective at penetrating this this protective extracellular polymeric substance layer. So these biofilms got this layer on the outside, and so it was able to higher that 2 parts per million was able to get through that biofilm, which initially led to an increase in the DBP formation, but it also killed off a lot of the biomass, and so long term we saw a reduction in the biofilms. So the pipe material that we have can also have an effect on our biofilms. In PVC water mains, chlorine achieves greater levels of inactivation in biofilms than chloramine. A concentration of 1 part per million of either free chlorine or chloramine has been shown to reduce HPC counts in coliform by more than 2 log in biofilms. Now, iron water mains are a little different because we often see a greater chlorine demand associated with iron water mains, and free chlorine residuals in iron water mains as high as 4 parts per million have been shown to be ineffective. So even at high levels, they can be ineffective. And then monochloramine residuals greater than 2 parts per million, however, have been shown to be successful in iron water mains at reducing HPC and coliform. So depending on what type of water mains you have, you may have to use different methods in order to achieve what you're looking to do. There's several studies that have been done regarding these, and in general, free chlorine followed by chloramines is the most effective strategy to reduce those biofilms. And then if you're looking at what effect flushing could have, the idea that you flush first and then you disinfect afterwards is deemed to be more effective in dealing with biofilms. But the thing, one of the important things is that you shouldn't just go out there and change your disinfection strategy without studying it, potentially pilot testing it. And definitely, if you're going to do something where you significantly change your disinfection strategy, I would recommend that you talk to your primacy agency. Some of these changes could require a permit, and you would definitely not want to do something without getting the proper permitting. And then once again, we've got an EPA technical guidance manual that helps with disinfection profiling and benchmarking. So now we're going to talk about sanitary surveys. And as I said, I spent some time, a little over 20 years with the state regulatory agency for drinking water, and so conducted some sanitary surveys. And I know that can cause some angst with operators, and hopefully that's not the situation you have with your regulatory agency where they're out to get you. I think in general the whole idea is that we try to work together to avoid problems. And so we'll just talk about some of the things that you might expect with a sanitary survey. So they're conducted by the primacy agency, and the idea is I've always deemed them not to be, we're going to come out and get you. It's working together. We're going to identify, what risks might be out there, because we want to make sure that the system's operating properly and that people are receiving safe drinking water. We want to make sure the systems have the capacity to do that, and it's an opportunity for regulators to get to know the operators and vice versa, and if there's any opportunities where we can educate or provide assistance, then that's what we want to do. A sanitary survey is an on-site inspection of a water system infrastructure, and it includes the review of plans, budgets, records, all sorts of different things. Now, why do regulating agencies do this? The primacy agencies do it it's required under the Safe Drinking Water Act. And so from a surface water treatment standpoint, there's a rule for that. And then also the groundwater rule, both of those require that they're done. Community water systems required every 3 years, and the non-community public water supplies every 5 years. So they'll just go through some of the elements of a sanitary survey. So we'll look at water source, the different treatment processes that you utilize, what your distribution system looks like, your finished water storage facilities, your pumps and controls. What are you doing the required monitoring? Are you reporting on time and properly? How's your system operated and managed? And then do your operators have proper certification? And so we go from source all the way through the distribution system, including some of these other components that make up those. So the process, what's going to happen? Typically before the survey starts, you will be notified. So you're going to get together all the records that the primacy agency may want to see, and you can expect that they're going to want to see a tour of not just a treatment facility if you have that, but also your distribution system, pump stations, look at the storage tank, stuff like that. And then afterwards, they're going to provide you with information about their findings. You know, good, bad, indifferent. They're going to talk about any sanitary deficiencies. And if you have any of those, they're going to give you they should give you a timeline to correct those. Categories, there's 3 different categories of deficiencies. They're significant. Those are the most important, the ones that could cause public health concerns or contamination. And then there's the moderate, which may not be immediate concerns, but could result in a significant deficiency if it's not addressed. And then there's the minor. Those are less serious, and quite often these are could be operational things that help the system operate more efficiently and perform better. So we got poll number 6. Which of the following do you think best describes a sanitary survey? A, where operators inspect and flush the distribution system. B, a survey to the public asking about drinking water quality. C, system inspection and review by the primacy agency under the Safe Drinking Water Act. D, review of community sanitary waste disposal under the Clean Water Act. Or E, none of the above.
All right, this one was answered pretty quickly, but I'll give everyone just a couple more seconds to go ahead and get your answers in. Closing the poll in 3, 2, 1. All right, Daryl. So the majority of people, nearly 3/4, said C, system inspection and review by primacy agency under CIDWA. And then we also had around 20% of people said E, all of the above.
All right. Well, and the answer is C, system inspection and review of the primacy agency under the Safe Drinking Water Act. Yeah, so that's what we were talking about. The operators inspecting and flushing the distribution system it really doesn't have anything to do with the sanitary survey. And we're not asking the public about drinking water quality. We definitely are not dealing with with community sanitary waste disposal. That's got nothing to do with the drinking water. sanitary surveys. So, so one of the, we'll look at different components. One of the components is the water source. And when we look at the sanitary survey, we're going to evaluate, you know, the safety and reliability of that water source. Can it be provided all the time, consistent? Is it a good source? We'll look at well construction. Are there any sources of contamination? How are we transmitting the water from the source to either treatment or into the distribution system? And if we look at some of the deficiencies, you know, these all show wellheads. So there's, you know, was the well constructed properly? Are wells, are they too close to surface water or sources of contamination? And then do we have adequate source water protection? Do we have means in place to avoid future potential contamination issues? So in this case, we've got a cap that's cracked, so things could easily enter into the well. In the second photo here, it doesn't extend to the proper height. Requirements for casings above grade are determined by individual state well construction standards, but 18 inches is typically the standard. So this is definitely not 18 inches above. And with the water ponding around on the photo to the right here, it's obvious that there's some flooding, and anytime we have that, the surface water could go down the casing and potentially enter into our drinking water. So that's not a great situation. So those are all potential deficiencies. For treatment, we want to look at how effective our treatment processes are to remove those contaminants that might be in our water. Those things can include disinfection and filtration, among other things. Some of our deficiencies that we might find, lack of monitoring points for chemical addition. So we're adding chemicals, but we don't have the proper places to check on our residuals. Are we storing our chemicals properly? Is there any cross connections between the chemicals, the waste flows, and the water? Have we had issues with MCLs or not maintaining residuals? And then lack of proper treatment or monitoring. So the chemicals are required. We require that any chemicals that are applied, that they meet the NSF standards. And so we are going to check on that. You know, in these photos, we have the potential for backflow. You know, there's a couple of things that are connected to this one here. This goes directly into the drain. So if this was hard piped, we've got a cross connection here. Some of the other things that we've looked like, I know of a situation that I encountered where, you know, little things like they had a day tank that they were able to overfill, and then that got into their wet well. And there's a lot of little things that we can look at with treatment when we come out and do these sanitary surveys that an operator who's looked at this for years might not notice because it's just normal to them. Another thing that is potentially a concern I've seen issues with is delivery of chemicals to a treatment plant where the chemicals are piped right in through the side of the wall and they get the wrong chemical. You could have you know, chlorine put into an alum line or something like that. So there's a lot of little things that, as the surveys, that we can see just because we're looking at from a different set of eyes when we come to look at a sanitary survey. The distribution system, there's a lot of, you know, the components, you know, a lot of things in the distribution system we can't see. So it's quite often we'll look at the things that we can. We'll look at records, you know, we may look at the pump houses and the pumps and the storage tanks and things like that. And generally, do you have a good cross connection program? Are you exercising valves? Are you maintaining and flushing hydrants? Are you replacing water mains that maybe you've had a history of breaks in, or you've got old main, cast iron, that type of thing. You know, maybe you can't provide the proper amount of flow, things like that. And we'll look at those things and maybe make some recommendations. You know, the age and material of water mains is important, the break history, things like that. Here we show a broken hydrant, fire hydrant, obvious. That's an obvious one. You know, if we've got these components could potentially flood, or it's not screened properly, things like that. Finished water storage is a difficult one. There's not a lot that we can see when we go to look at those. We want to look at, you know, any security things. That's one of the easier ones to see. Do you have the proper security measures in place? Do you have the right screens? Are there openings in the tank that things could get in? Damaged screen or overflow pipe there, and then, you know, the proper screen size. There's not a lot that can be seen with one, but we're going to look at them nonetheless. As far as pumps go, are they functioning properly? Do you have redundancy? Do you have enough, you know, the proper number of pumps that if they're out, you provide firm capacity, things of that nature. Here's an example. We've got 2 pumps, so we have redundancy, assuming that, you know, one of those pumps, each of them is the same, and they're able to provide enough. On the right, we've got a flooded pump meter pit. That's not a good situation because most of the meters are typically not set up to be underwater. So if you don't have pump capacity, you don't have redundancy, if your pumps cycle too frequently, then that could be a sign of an issue. Either maybe you don't have enough capacity, or maybe there's an issue with a check valve, maybe the pump's going on you. Screening for pumps, if you've got histories of outages or low pressures. And then we're going to look into the operator compliance. We're going to look at, you know, do your operators have the proper licenses? Are they qualified? Do they receive proper training to maintain their licenses? Do they know what it takes to operate and maintain the water system? So proper operator certification and type and level for the system. Some states require different types of levels or different types of certifications based off what you're doing, along with levels based off of your size, size of your community, population, or how much you treat, things like that. So yeah, so do you have enough people to operate the system? And then you should have documentation of that. You know, if you're doing training, you should be able to document that your operators are being trained. So management and operations, we're going to look at the overall management, operation practices of the water system. You know, are you planning for any future financial needs? Do you have a capital improvement plan? Do you keep records on all your stuff? Are you planning for those contingencies? You know, what might happen in the future? And some of the aspects of that, you know, your policies and your ordinances. You know, a lot of that can be out there, and that ordinances can help a system to do what they need to do. If you don't have a good ordinance, you may not be able to have a good cross-connection control program or something like that. How's your system managed? You know, in a lot of cases, the water, the money that goes to the water system should stay with the water system and not be used for other things. What's your system area? You know, who do you serve? You need to know those things. Are you planning for asset management? Do you have emergency response planning? If something comes up, do your operators know what to do in a case of an emergency? Is it all outlined in a plan? Do you notify the public of things like violations and stuff like that? Are you doing that properly? Do you, your consumer confidence report, your annual water quality report, are those being properly, is that information being properly conveyed to your customers? Are you maintaining your cross-connection control records? And then you should, all these things you need to keep on hand, and you should be prepared to provide them to the primacy agency when they come out to do the sanitary survey. And that includes, records of previous sanitary surveys, any permits that you may have received. Typically, there's a record-keeping requirements in the statutes, individual states may have, that indicate you need to retain records for a certain amount of time. And the most, common problems that water systems have is, lack of a current functioning environmental or emergency response plan. So quite often what happens with emergency response plans is they get created and then they never get touched again. Nobody updates them. If you've got a contractor that you use and that contractor goes out of business, quite often that they're not updated and replaced. Operators, they retire, they move on. And the other thing is having enough income, having the rates set up so that you're able to do what you need to do. You're able to plan for capital improvements, make necessary repairs to your system and upgrades and things like that. So I mentioned a little bit about keeping the monitoring or the reporting and monitoring up to date. So we're going to look at, a lot of this stuff. I think the monitoring reporting gets reported throughout the year, based off my understanding, my experiences. It's not something that you would probably be surprised by at a sanitary survey, because the primacy agency is probably going to let you know if you're not providing them with the information that they need. But they'll look at your practices, your sampling plan, whether it's your bacteriological site sampling plan, your disinfection byproduct plan. How is your laboratory procedures? If you're doing in-house laboratory stuff, are you using a certified laboratory if you're required to for external stuff? Are you measuring your chlorine residuals when you're collecting your bacteriological samples, things like that? So yeah, some of the sampling plans, coliform DBPs, the lead and copper rule sampling, water quality factors and treatment process control. So that's, checking to make sure that your treatment's being done properly through different sampling throughout the treatment chain, submitting any compliance monitoring results and records, disinfection residual monitoring or use of approved laboratories, calibration of instruments if you're doing, could be for residuals, could be for in-house laboratory testing, and what sampling procedures you have. So poll number 7, which of the following do you think is a tier 1 sanitary deficiency? A, an operator has not attended a training in the last 10 months. B, end of tank overflow pipe is 20 inches from the concrete pad. C, a well casing does not have a sanitary seal. And D, the system is understaffed.
All right, the majority of people have entered their answers, but I'll give everyone just a couple of more seconds to get your answers in, and then I'll be closing the poll. All right, closing the poll in 3, 2, 1. All right, Daryl. So the majority of people at 84% said C, A well casing does not have a sanitary seal.
Okay. And that is the correct answer. Just to cover the others, just because an operator hasn't attended a training in the last 10 months does not mean that they still may be fine with their certification. Tank overflow pipe is 20 inches from the concrete pad. That may be sufficient. We don't know. And the system being understaffed, although that's a problem, we're talking about the worst of the worst, and a well casing that doesn't have a sanitary seal could allow contaminants to enter the water, and that could threaten public health. So that's why that it would be the right answer. So now we're going to look more into sampling and monitoring, go into some more details about that. So we've got a system and we're adding chlorine, and so why do we want to monitor that chlorine residual? So there's a few different reasons why we might. Well, first of all, there's a maximum residual disinfection level, so we can't apply too much. If we do, then we've got problems with our primacy agency. So we want to apply less than 4 parts per million. And then we also want to maintain a minimum residual out in the distribution system. The minimum recommended residuals here, 0.2 parts per million for chlorine and 0.5 part for chloramine. I would recommend if higher than those, but you use this information to make sure that you're operating the system properly. You need to collect chlorine residuals when you collect your routine and repeat chloroform samples. So if you're chlorinating and you're collecting those samples, you have to collect chlorine residuals at those same times. The information helps you ensure that you're protecting against the pathogens. If you don't collect the information, you don't know. You'll be able to be more certain that you're inhibiting that growth of biofilms if you collect your residuals. If you don't have the information, you just don't know. And then it's also an early warning sign if contamination exists, because if you see a reduction in residuals, then it could be because you've got contamination out there. And then it's to ensure, you want to ensure that you've got that residual of at least 0.2 parts per million in the remote sections and dead ends, so the worst areas of the system. And then how do you monitor chlorine disinfection residuals? The most often used method is the DPD method. And as you see, that's that big, long word. That's a reagent, and what it does is it reacts with the chlorine that's in the water, and it gives you an indication of how much chlorine residual you have. So if you see here on the left, it's a blank sample, there's none in there. It gets, as we go from left to right, as there's more chlorine, it becomes a brighter, pinker, color. And then this one on the right signifies that there's so much chlorine in there that it's actually taking the color back out. It's bleaching it out. So we use this, we look for a change in the color. We can test for both free residual and total residual. Quite often people will use these little pillow packs. You tear it open and you put that in the bottle. As you can see, there's an example of the pink color that comes out. Those bottles get thrown into a little handheld meter that will provide you with a number, result. And then the old school way was these color wheels. And so the idea was you would match it up with a known amount. These, I think, are pretty much phased out. I'm sure there's people still using them. The problem with them is that in sunlight, these would fade. And so quite often operators are out there, they throw them on the dash of their truck, and before you know it, they're all faded out and not giving you accurate results. So I think we said, through time and temperature, there's a lot of things that can affect our chlorine residual. And this just shows kind of a study of a system where they took samples in different months, and they showed just how the chlorine residual dropped. What's typical is that the warmer the water is, you may have higher residuals, but they drop faster than you do with colder water. And if you're looking at, in this instance, a good portion of these at 0.2, that level that we said you should maintain, they're getting it was only about 7 hours that it took to drop that much. And that's, this study was done in Chile about rapid chlorine residual decay. And I mean, if within 7 hours you're going to lose, you'll be down to 0.2. That's pretty difficult to operate. So you want to flush the sediment from the pipes, maintain a scouring velocity when you do that. You may need to replace, or line pipes depending on what you've got. Cast iron pipes can definitely eat up our chlorine residuals. And then, the newer the water you have, you can see from this, the higher the residuals. So if we can turn water over and try and reduce water age, that's beneficial. So this is from a study that was done in Korea, and they were looking at the potential to have to boost chlorine out in the distribution system. So as you can imagine, that could be a problem, because the potential for creating disinfection byproducts increases because you're adding more chlorine out into the system. But the darker areas, had more chlorine to start with. Here we had 1 part per million as it entered the system, and we got out into the system, we were seeing at dead ends 0.01 and 0.05, and that's at the point where it's almost not measurable. So yeah, they did this study to see if they needed to add booster disinfection out in the distribution system. But we can do things. We can flush dead ends. It's possible that that booster chlorination is an option, but once again, like I said, the potential for forming disinfection byproducts makes it, you really have to study it pretty hard to see if it was worthwhile. Monitoring the pressure out in the distribution system is helpful as well. We want to maintain that pressure of at least 20 psi, 35 psi under normal working conditions, I would recommend. But it helps to avoid those back siphonage and backflow issues that could potentially be out there. Any leaks in the water mains if we have lower pressures. We want to make sure we have pressure for fire flow. And then the higher points in the system, as we talked about pressure yesterday, the pressure is going to be lower at higher elevations. So we're on to poll 8. Which of the following water quality management practices specifically helps to reduce chlorine demand? A, gently flushing dead ends. B, maintaining pressure above 20 psi. C, ensuring tank turnover of 5 days or less. Or D, system flushing and tank cleaning to remove sediments.
All right, so the majority of people have entered their answers, but I'll give everyone just a couple more seconds to go ahead and get in your answers. Closing the poll in 3, 2, 1. All right, Daryl. So the majority of people at 85% said D, system flushing and tank cleaning to remove sediments.
Yes, and that is correct. Because that actually will affect, it'll help to reduce that chlorine demand because you're getting the things out that could potentially eat up that chlorine. So now I want to talk a little bit about the revised total coliform rule. And there's two aspects about it that are most, I guess, most important, and to understand the repeat sampling requirements and are in the required number of samples based on population. And so, so if you get a routine positive total coliform out, you need to take at least 3 repeat samples within 24 hours from the following location. So you got to collect a repeat of the original site. You got to go within 5 service connections upstream and within 5 service connections downstream. So, and then the groundwater rule would then also require that if you're a groundwater system, that you collect a set of all the raw water well samples that were operating when that positive, all the raw water, the wells that were operating when that sample was collected or before it was collected. And the number of samples is based on population. So the number of samples required each month is roughly 1 sample for every 1,000 persons served. But we're going to give you a table that'll show more details. And and if you're a groundwater system that serves under 4,900 people, you can collect all your routine samples on the same day. But if not, if you're larger groundwater system or surface water, you've got to space them out throughout the month. And there's a link to the reference guide for that. It's a very helpful one. And this is from that, and it shows just the different population breakdowns. As you can see, the more people that you have in that you serve, the more samples that you're going to have to collect in a month. And this is an example of a sample siting plan. The sample locations need to be representative of the distribution system. You're going to identify your routine sample sites. You're also going to identify your repeat sample sites. And as I said, those have to be within 5 service connections upstream and downstream. And then some of the concepts about representative. So we talk about it being representative samples. We have to look at different population centers. We have to look at different pressure zones. If there's different geographical areas, this is separated. There's a river, and so you've got, in essence, 2 systems, something like that. Or if you've got different sources, where is the water coming from? All these things need to be taken in consideration. We're going to look at this example here and to show what we mean by routine and repeat sites. So in this case, we've got our routine site is 123 Groot Drive, and our repeat sites are 100 and 189. If we look here, 189 is 1, 2, 3, 4, 5. It's within 5, so it's the 5th location, and that's our downstream in this case. And then our upstream is 100, so that's going to be 1, 2, 3, 4. So that's within 5 as well. So these are valid sample sites for our sampling plan. So further on the revised total coliform rule, as part of that rule, initially we had just the total coliform, and then it became the revised total coliform. As part of that, the E. coli was added as an MCL. So if you get an E. coli, you've got a maximum contaminant level violation. And the whole idea is that we're incorporating a find and fix approach. So we're gonna, if we've got problems with coliforms, we're gonna go out and we're gonna figure out what they are so that we can correct them. Whatever might have led to either total coliform or E. coli positives. And a level 1 assessment is the onus is put onto the utility to investigate any potential sanitary deficiencies, and that is required once there are 2 or more total coliform samples in a month. If you're a system that collects less than 40 routine samples in a month. and if there, or when there's greater than 5% of the samples. So if you collect 40 or more routine samples, when you have 5% or more that come back total coliform positive. And then the level 2 assessment is performed by the primacy agency, and that's when the utility has had 2 level 1 assessments within a 12-month period, or you have an E. coli violation. So until you get to that point, it's on the utility to do the investigation. And then you get in that spot where you've had 2 within a 12-month period or an E. coli violation, then the state's going to step in and they're going to do an assessment. So the idea is that for contamination to occur, there has to be a source of contamination. There's got to be a pathway for that contamination to enter the system. And then there needs to be a mechanism that causes this contamination to enter the system. And there's a RTCR, quick reference guide. So just a quick thing on how to collect a coliform sample. This is a typical coliform sample bottle. You'll note in the bottom there's this little tablet. That's the dechlorination agent. Sodium thiosulfate is commonly used for that. And so the cap should have a seal on it. The cap's there. If you don't have a seal on it, you should get a different bottle. Don't use a bottle that isn't sealed. Looks like it's been tampered with. When you collect the sample, you hold the cap down, fill your bottle, put the cap back on. You're aiming for this line right here to make sure that you put that 100 ml line to make sure you got the right amount. You want to make sure that sodium thiosulfate tablet's in there to dechlorinate. It will take the chlorine out of the water. Some of the tips for collecting a sample: avoid taps that have threaded spigots. Anytime you've got threaded spigots, there's the opportunity that there's something caught on that. Could be something organic, microscopic, or and maybe that somehow gets into your water. And that's not really, it's not representative of your actual water in the inside tap. It's just comes off. You want to have that tap at least 18 inches above grade. You want to run the water until it cools. So you want to see that temperature change. If you have the right type of spigot, you can use alcohol on it to kill anything on the outside. You could, in some cases, ideal, you can torch it. You can put a flame on it, and that'll kill anything that's on the outside of the tap. And an ideal one is a stainless steel gasketless valve with a downturned spigot, and with copper tubing. That makes a great sampling tap. Now we're on to poll number 9. Why shouldn't a coliform sample be collected without having a dechlorinating agent in the sample bottle? A, the chlorine could damage the plastic bottle. B, nothing, just write this on the chain of custody. C, the sample would not be representative. Or D, it would result in a false positive test.
All right, the majority of people have their answers in, but I'll give everyone just a couple more seconds. I'm closing the poll in 3, 2, 1. All right, Daryl. So the majority of people at 63% said C, the sample would not be representative, but we did have a third of people also say D, it would result in a false positive test.
All right, thank you. So actually, the answer is C. The sample would not be representative because there is the potential that chlorine there would be chlorine in that bottle, and it would still be allowed to act on anything that was in the water or in the bottle. So so it wouldn't be representative. As far as it being a false positive test, it would be less likely to be positive. So it's not really, it wouldn't result in a false positive test. If there was something in there, it would be in there. So yeah, so therefore the sample would not be representative of the quality. All right, so the next topic I want to cover briefly is the lead and copper rule. It establishes action levels for lead and copper. There's been a lot of talk about lead and copper in the last several years. We've got some states that have even instituted even more stringent action levels. And it's based off the 90th percentile level of tap water samples. So that's if you had 10 samples, it would be the 9th from lowest to highest. And the sample is a first draw from a tap that sat unused for at least 6 hours. So we were trying to get the water, it's supposed to be representative of the water that's in the home. And there's the standard frequency for sampling is every 6 months. It can be accelerated or reduced depending on the results that you get. And AL exceedance is not a violation, but it can cause you to have to do other things. You might have to do water quality parameter monitoring, corrosion control treatment, or study. You may need to look at your source water or what treatment you're doing, issue public education, or very likely if you have lead service lines, you'll have to go through replacement of those if you are not already doing those. And so we've got a couple of reference guides for those shown at the bottom. And lead copper sampling in tiers. So this is much like the how many bacteriological samples you have to collect. Lead and copper is also based off the system size, as you can see here. And they're standard and reduced numbers. So standards are reduced are typically half of what the standard are. Water quality parameter sites and requirements. Once again, you have standard and reduced. It's just to give you an idea of how this is all decided on, how many samples that you have to collect. And then there's the tiered system. So you want to collect those samples ideally from tier 1, which are single family with homes with copper with lead solder constructed between 83 and 88, or lead pipes including goosenecks or pigtails and or lead service lines. If you don't have enough to meet your standard or reduced numbers, then you would have to go to tier 2, and you're going to look at all building types, not just single family, with the same set of standards. And then if you don't have enough tier 1 and tier 2, then you look at single family structures that have copper with lead solder constructed before 1983. And then if you don't have enough of those, then you go to basically everything else. So you have to you collect from tier 1 if you have them. If not, you go to tier 2, as many of those. And you move down this. If you don't have enough, you'll eventually get to the bottom. So there's a chart also for the disinfection byproducts rule. As I had said, that's based off this locational running annual average, which is a little different. And THMs and AHAs form when we've got those organics in the water and the chlorine reacts with it. Now, bromate, there's requirements for bromate, and those requirements are based off of, those are for systems that use ozone to disinfect, because if you've got bromide in the water and you use ozone, you can create bromate, which is another thing that's regulated. And then if you use chlorine dioxide, which is another form of treatment, then you can form chlorite. So you may have to, if you're using chlorine dioxide, you would have to test for chlorite. And there's a quick reference guide for the disinfection byproduct rule as well. So as you said, compliance for THMs is 0.08 parts per million. For HAAs, it's 0.06 parts per million, and that compliance is based off that locational running annual average. So every location that you test at has to meet that independently. And then how do we determine what these sites are? That was based off of when the rule went into effect or a system goes online, they would have to do this initial disinfection, the distribution system evaluation. And the idea behind that is you're going to look at your distribution system and you're going to try and find the places that are most likely to form this disinfection byproducts. And that's where you're going to have to sample. So the idea is that it's the worst case locations. And this is just purely to give you an idea of some of the things that you might have to do when you collect these samples. HA5 bottles have a preservative, so you have to wear gloves and eye protection. You don't want to rinse that stuff out. Similar to the dechlorinating agent in coliform bottles, you're going to fill within, I usually say, to the neck of the bottle, and you have to keep them on ice. THM samples a little different. These are vials, and you want to have no air in them. Ideally, a little water bubble when you put the cap on, and they are time dependent and temperature dependent. So here's the sampling chart for THM and HAAs. Subpart H are the surface water systems, and then we have groundwater. As you can see, based off population, there's different requirements for stage 1 and stage 2. So here's a groundwater system between 500 and 10,000. You know, their frequency is annual, and they've got to do one per treatment plant. Stage 2, they've got to do annual testing, and they've got to do 2 distribution system monitoring locations. So poll 10, what is the maximum contaminant level for total trihalomethanes that is allowed in drinking water?
All right, the majority of people have put in their answers, but I'll go ahead and give everyone just a couple more seconds to get their answers in. And closing the poll in 3, 2, 1. All right, Daryl, so the majority of people at 73% said D, 0.08.
All right, well, thank you, Kristen. And 0.08 milligrams per liter, parts per million, that is the correct answer. So I want to talk just briefly about we're collecting samples, the importance of a chain of custody. So chain of custody is when you collect those samples and you take those to a laboratory, you need to complete a chain of custody, and it's going to identify the sample with the date, time, and the location where you collected that sample. You know, we're going to have information about the sample source, any preservatives that might have been used, what kind of testing we need to have done on those samples. Each time if you transfer it to, say you've got a courier that comes and picks that sample up from your DBW, and then they have to sign off on it, and then they take it to the laboratory. It needs to be signed off. So there's a chain showing who's had custody of those samples. And then you need to make sure that you're using the proper storage, preservation, any temperature, you know, ice, that type of stuff. There's the lab verifies that the chain of custody, the records and the date and time of receipt, everything, all the information. They make sure that nobody's been tampering with the samples. And then typically those results are sent back, or a copy of that sent back with your results. It's something that they maintain and you should maintain as well. And here's just an example of an example chain of custody. You can see up at the top the information about the water utility, who sampled them, signing off, you know, what times, where locations, was it a grabber, composite, how many containers you had, what analysis are you requesting, what do you want to have it tested for, and then you know, how many containers and who had access to those, who's signed off on those, information about how many coolers you had, what was the temperature of those. That can be very important, especially with these THM and HAA samples. So now if you've come up with an issue and you've got to notify the public, there's a set of different tiers that it's important to know. And the tier 1 that's an immediate notice, and that's a serious situation, potential for human health concerns. You've got to notify the public within 24 hours. And usually it's the stuff that goes over the radio, the television, in the newspapers, that kind of thing. It's very urgent. Tier 2 is, you know, we exceeded a standard. We had an MCL, but it's not anything that is immediate concern for the public. You've got to do that within 30. You got to notify public within 30 days, and that could be via the media posting or through the mail. And then the tier 3 is the least restrictive. That's an annual. It's a standard that doesn't have a direct impact on human health. You're given up to a year to provide that notice. Tier 3 should be provided in the same way as Tier 2 public notices, but quite often people can, it's helpful that they can just include these Tier 3 notifications with their annual water quality report or consumer competence report, whatever you call it. So what are the 10 different elements of a public notice? You had to describe the violation that occurred, including the contaminants and the levels. When did it happen? What are the potential health effects? And there are lists of those you can go and find. Who's the population at risk? You know, are there any particular people that what is it, babies, different things like that? Should they find a different source of drinking water, you know, as part of this? And what's the system doing to fix the problem? Any actions that the customers or consumers can take, and then when does the system expect to have the problem resolved? You need to put information on there as to how to contact you for more information. And then if you've got, you know, if you've got non-English speaking population, you may want to put it out to them, and you also want to have people share it with people who may not normally get the public notice. And there's information on that. Tier 1 notice is required as soon as practical, but no longer than 24 hours after you learn about the violation or situation. And those are typically things like E. coli or fecal coliform violations, nitrate or nitrite MCL violations. We talked about that earlier. Chlorine dioxide maximum residual disinfection level violations. If your surface water plant, if you exceeded your maximum allowable turbidity level, that would be one. If you found out about any water disease outbreaks or emergencies, if you detected E. coli, enterococci, or coliphage in a groundwater source sample, so that's at the source, that means you've got a problem with your groundwater source, or other violations or situations determined by the primacy agency. So the primacy agency can tell you that you need to do a tier 1. And that's why if you run into any of these situations, you should definitely be in contact with the primacy agency so they can help you through that. And there's a quick reference guide for that. The Consumer Confidence Report is due out every year. It covers the previous year, due in July, I believe. And see, these are just some of the components. This is what an example might look like. And then you also have to follow these reports up. You send these out to your customers, but they have to follow up with a certification to the primacy agency within 90 days of it. You've got a violations column. You've got a contaminant column. You've got, they're organized by types. So different types of contaminants. If there's a more stringent state requirement, that should be identified. There's a column to show the MCLs for the different contaminants and what your results are. There's a table key to help people understand it. And as I said, it's due out by July 1st each year. So if you're doing it for 2020, in July of 2026, it would be the 2025 information. And work with your primacy agency if you've got any questions. And there's a quick reference guide for that. And then our final poll: what public notification procedures are required when a utility learns that water tests show positive for E. coli? A, Tier 1 and boil water PN issued ASAP within 24 hours. B, you must notify within 1 year, including full lab procedures. C, a public notice is not required for E. coli, but disclosure required if asked. Or D, do not drink notices are sent via mains to customers' sinks.
Right, that one was answered very quickly. But I'll give everyone just a couple more seconds to get their answers in. Closing the poll in 3, 2, 1. All right, Daryl. And 98% of people said A, Tier 1, and boil water PN issued ASAP within 24 hours.
All right, thank you, Kristen. Yes, I'm glad that everybody answered that, because that is the correct answer. Obviously, it'd be interesting to see do not drink notices popping out of their sinks. That would be a funny one. So what do we cover today? Disinfection, dosages and feed rates, disinfection byproduct prevention, sanitary surveys, sampling and monitoring. We've got these takeaways. We want to keep in mind water age management, what our sampling and monitoring practices are. Disinfection is a very important thing for water system operators. And we want to thank you for participating. I don't know if we have any questions, Kristen?
Thank you, Daryl. We have not had any questions come in yet, but if you do have questions, then go ahead and get them in while we still got Daryl around. We also are joined by Greg Pearson, who was here yesterday. So go ahead and get your questions in if you have any. We've had some compliments coming in. Someone said great webinar. Someone else said great information and very practical on chlorine dosing. So kudos to you, Daryl.
Thank you all.
All right. Well, I think we've given everyone enough time to get their questions in if they had any. But your information is also on the screen still. So if anyone does come up with any questions, feel free to reach out to either Daryl or Greg. A huge thank you to Daryl and Greg for joining us yesterday and today for this virtual workshop. Following this workshop, each of you will receive a follow-up email with a link to the recording. And we ask that you please fill out the feedback survey that will be arriving to you via email after this webinar. Thank you all for attending, and we hope to see you at future EFCN events.
Thank you all for attending, and thank you, Kristen, for monitoring this webinar. I very much appreciate it.
Absolutely, my pleasure. Thanks, Daryl. You'll have a great day.